Hello everyone and good evening. Welcome to the OneClass channel. My name is Fejiro and I'm an honors Bachelor of Science graduate and currently working towards medical school. For today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some homework help or some extra help with tutoring, check out the links in the description below. With that being said, we're going to kick it off with this session. Give me a quick second to set that up here. We're going to have starting here, and we are good to go with question number 1. We have decide whether each molecule or polyatomic ion is polar or nonpolar. So for the first question, decide whether each molecule is polyatomic, or each molecule or polyatomic ion is polar / non-polar. Okay, so with this it looks like the student had already gone through the question, but just so we review this to understand what it means to be polar and non-polar, it helps to be able to draw the Lewis dot diagram. Okay, so with that being said, they give an example of what they're looking for. So if it's polar, you want to write the chemical symbol of the atom close to a negative side. So HCl, for example, in the example give, they have HCl. This is a polar ion, okay? Because chlorine is where the negative is going to be. Okay, it's going to be, well, it's going to be the pseudo-negative part, okay? And hydrogen is going to be more positive. And this is based on the electronegativity difference. But with that being said, the reason why they say you enter hydrogen is because chlorine is your quote-unquote negative side. So the atom closest to that negative side is going to be here, because chlorine cannot be close to itself. It is itself. So that's why they say you use hydrogen there. So with that being said, let's go through this question to see whether it's a molecule or a polyatomic ion. So we're going to start with CH3F, okay? So we're going to put carbon in the middle, okay? And this is what CH3F looks like. You can even check this by making sure you have the right amount of electrons. So carbon would be able to donate 4. There's 3 hydrogens, so that's 4 plus 3. And fluoride has, fluorine has 7 electrons. So 7 plus 4 plus 3. In total, we do have 14. So our Lewis body diagram should also have 14 electrons. And we can check, we have 8 surrounding the fluorine, and then plus 6 more. So indeed, this is going to be our Lewis dot diagram. So now we see, based on the, if we look at the periodic table again, fluorine is actually one of the most electronegative elements, actually. So it has a whole electronegativity of 3.98, while carbon is 2.55. We can't do the math, but we can see just by visual that it's going to be greater than 0.3. And the reason why it needs to be greater than greater than 0.3 difference is because this is what defines it as a polar bond, okay? Polar bond. And this is important because if fluorine is the only one here, there's nothing that really counteracts it. The hydrogens actually have a much less electronegativity as well. It's just 2.20. So that being said, the greater the electronegativity, the greater concentration of, I guess, electrons there'll be there. It'll be the more negative end, okay? So for this, we can actually make this the more negative. Now, the second part of the question, it asks, which is the atom close to it. Because of that, it would actually be carbon. Carbon will be the the atom closest to the fluorine, because fluorine is a negative. So the atom close to the negative side is the one attached to it, and that would be the carbon, not the hydrogens. So with that being said, for the first box, it'll be, so if we actually just maybe and do that, CH3F, we have the first answer. It is indeed polar, and the atom close to it will actually be carbon. Okay, so now let's move on to the next one, F2. Okay, so this one, when we draw it out, remember that fluorine has 7 electrons, so if we add them together, we're working with 14 electrons total. So Lewis dot diagram for fluorine molecule would just be like this: 1 bond between them, and then following the octet rule. And if you added all the electrons, it should indeed equal 14. Now, as we're saying, because now they're the same molecule, actually in this case, the electronegativity difference will just be 0. So there wouldn't be a positive or negative side based on this molecule. So that being said, because there's no positive and negative side, there's no direction of where it will be attracted to. This would be considered non-polar. Okay, and now which is the atom close to the negative side? It'd be nothing. It does not apply here. In fact, it'd just be better to just put Na. Okay, not applicable. Now for the last one, NH2 minus. Okay, so for this one, let's just do a quick recap. Nitrogen has 5 valence electrons, and each hydrogen has 1 valence electrons. But there is a minus sign, meaning that we have 1 extra electron to work with. So if we have 5 plus 2 hydrogens, that's 5 plus 2, plus that 1 more electron. In total, we're working with 8 electrons. And if we drew it out, it would look something like this. That would be NH2 minus. Now, as you can see, it fills the octet rule, so we're set there. Okay, and in a sense, what nitrogen would typically look like is like this, because it would have 5 valence electrons, and 2 of the 5 currently are being shared with a hydrogen, which provide 1. So that now that extra electron can just fit right there, allow nitrogen to meet that octet rule. So now with that being said, to make sure that our charge is going to be on the nitrogen, we can actually use formal charges here. So nitrogen, the formal charge, the way you calculate it would be 5 valence electrons minus how many electrons it has by itself, so it's lone pairs, but individually, so that'd be 4 electrons total, plus how many electrons it's sharing. So it's sharing 4 electrons, right? But we have to divide that by 2. So that being said, we have 5 minus 6, which is minus 1. So this nitrogen does indeed have a charge of minus 1 right here. So that would be the most negative side, okay? And you can tell right away, because of the lone pairs, right? These aren't evenly balanced, okay? These lone pairs, well, the nitrogen itself will have its own pull. Looking even at the periodic table, you see nitrogen has an electronegativity of 3.04, and hydrogen is 2.20. So that is still greater than 0.3. So that is a polar bond between the nitrogen and hydrogens. In fact, it's a specific type of polar bond known as hydrogen bonds. But nonetheless, we can still say exactly that it's a polar molecule, okay? And the atom closest to a negative part will be any of these 2 hydrogens here, because as long as they're touching nitrogen, which is the negative part, the hydrogens are the ones closest to it, okay? So this would be how you approach this question. This is a quick breakdown of what we did. You first have to really understand your Lewis dot diagram, so you can just do quick sketches as what I did. And then you have to know how to identify where your negative side would be. This is done through the electronegativity. Okay, that's very key and important. Even if you weren't sure about the Lewis dot diagram, as long as you can maybe get a I guess a picture in your mind of what things connect to each other, you can calculate the electronegativity difference, allowing you to see if it is a polar or a non-polar molecule based on how it can balance out. Okay, and the last part, just the atom close to the negative side. With that, just make sure that you always attribute the negative side to the one that has the greater electronegativity. Okay, and if there's a big enough difference, that's when you say, okay, this is just more negative. All right, so that is how we solved that question. Let's see how we did. Yep, CH3F is polar, and the closest one is a carbon. F2 is nonpolar and not applicable, and NH2 polar and is a hydrogen that's the closest part. So this is correct. Hopefully we were able to break down this question sufficiently, and if you had any parts of pause, you can always just go back and just play it again just to see how we were able to get to this answer. With that being said, let's move on now to question number 2. Okay. So for question number 2, we have, what are polar and nonpolar covalent bonds? So this is more of a conceptual questions. It's not asking you to identify anything, just asking you what they are. What are polar and non-polar bonds? Okay, so for this question, okay, this, we're going to actually get the help of what they answered with, okay? The important part I'm going to highlight right away is the electronegativities, okay? Because they're not talking about polar or non-polar molecule, okay? They're talking about the bonds. Finding out a polar or non-polar molecule requires a little bit more work, where you have to really get the bonds all together and get the visualization and see if there's an imbalance, and they can identify this is a polar molecule or not. Now, just to identify the bonds, that one is specifically about the electronegativities as I've highlighted, okay? Specifically the electronegativity difference. Electronegativity difference, okay? That is what we're using to find out what polar are and which ones are polar or non-polar bonds, okay? So I'm going to break it down the different cutoffs for each one. So typically, when your electronegativity difference, okay, I'm going to call that ED. So ED is less than 0.3. That is going to be non-polar, okay? When your electronegativity difference, okay, so we now have between 0.3, okay, and less than 1.6, that is going to be polar. And now 2.0, if it's greater than 2.0, that means it's ionic. But that one's a little bit tricky. I'm going to add an asterisk to it, because anything greater than 1.6 and it's a bond between a metal and non-metal also counts as an ionic bond. So just make sure you have to watch out for that, because there are quite a bit of variations between them in regards to that. So now with that being said, you're probably wondering, what does electronegativity difference mean? So the electronegativity difference, or just electronegativity, is kind of like its affinity towards electrons, okay? So you'll see when you look at the periodic table, typically the relationship, if you go look at the periodic table like that, the relationship for the electronegativity goes kind of this way, with fluorine right here being the highest one, and I think it's like radon being the lowest electronegativity. So the reason being because, well, let's start with noble gases. Noble gases, they're content with the amount of electrons they have, so they don't really have an affinity towards more electrons, so that's why they're not really counted. But fluorine, exactly, it really wants another electron. Like, that is one of its almost primary purpose. It will always try to take away electrons from other places and other atoms. And radon, on the other hand, actually really doesn't care if it has one. In fact, would want to, as easy as it can, just give it away. Like, it has no affinity towards it. Looking at the periodic table, you'll see here exactly. We have, so it's actually francium, not radon. So francium, radium is right here. Francium is the one that has the lowest electronegativity of 0.7, and fluorine has 3.98. So as you're calculating the electronegativity difference, what you do there is you subtract the lower number from the greater number and see what you have left. You can do it other way, but you have to make sure you get the absolute value because electronegativity difference is always done in its positive value. That's really the only way it makes sense. And then you're able to see which criteria it falls under, whether it's nonpolar, polar, or ionic. Because the question is talking about polar versus nonpolar covalent bonds, this would be the difference here. It would be the electronegativity difference, specifically between the ranges, well, 0.3 serving as a cutoff. Less than 0.3 is nonpolar. Greater than 0.3 is going to be polar or maybe ionic later on. But yeah. And just as how it says here, I'm going to touch base on even what it means to be nonpolar versus polar. So nonpolar would be when there's no, I guess when there's little electronegativity difference. It means that they both have around the same affinity for electrons, which is why the electrons will be evenly shared amongst them. For polar, before we get to ionic, one side would just will have the higher concentration ish of electrons, as in the electrons would prefer to hover around there more, the one with a greater value. If the difference is enough, the electrons would actually prefer, or specifically the atom itself would actually prefer to have more electrons surround that atom. Okay, so as they show here in this example, CH4 methane is a nonpolar covalent bond because actually the difference in electronegativity between carbon and hydrogen is actually like almost around exactly 0.3. Okay, so that's why we don't count that. Let me just double check here. We have, or is it 0.4? I think it's 0.4 as a cutoff. There we go. Because you'll see here, C and H is, you have 2.55 and 2.20. You have 0.35. Yeah, it is 0.4. So, in fact, even when we do this, I would always check with your instructor because they do have specific rules they follow, like this whole polar versus ionic. Just make sure that whatever notes you're given, you follow that, because that should answer what is determined as a polar or non-polar bond. Okay, so CH4, that is non-polar. H2O, the electronegativity difference there is actually quite drastic. So oxygen has the electronegativity of 3.44, and hydrogen is still 2.20. So it's like a 1.24 difference. So it definitely falls in range of what we define as polar. And so the oxygens will kind of have an affinity for the electrons present between the oxygens and the hydrogens. So that is how that is a polar bond, okay? So that being said, that is correct. Let's move on to question number 3. So now we want a Lewis structure of PBr5. Okay, so for this, we definitely first need to know how many electrons we're working with. So we're going to go to our handy periodic table. Okay, so phosphorus is right here on the 15th column, so you could say that it has 5 electrons. You could also figure this out by doing the electron configuration. So if I just did the shorthand right now, okay, we'd start with neon, and it'll be 2s2 2p3. Okay, and that shows right there in its valence electron, its outer shell, it has 5 electrons. Now with the Br, similar thing here, but it's actually just going to be one row down, and it's going to be on the 17th column. Okay, so with that being said though, because it's on the 17th column, I would still say mostly likely has 7 valence electrons, and we can actually see this when we do this. So we have, it'd be argon, because when we start for bromine, okay, and then we're going to do 2s2, whoops, sorry, already passed that row, and this will be 2, that actually be 3. 3s2, 3p3, it's on the 3rd row, and this would be 4s2, 3d10, because it's passing through the transition metals, and then the 4p5. And because the 3d10 is done in the 3rd shell, we only count these 2, so 2 plus 5, that's definitely 7. So now we know that phosphorus has 5 valence electrons and bromine has 7. Okay, so now we need to figure out the actual Lewis structure. Let's see how many electrons we're working with. We have 5, okay, plus 7 times 5. So that's 35 plus 5. That's 40 electrons total that we're working with, okay? So with that being said, let's start drawing it out. Now, phosphorus is the only individual one, so I'm going to start there. I'm going to just take a quick guess here, actually, because phosphorus has 5 valence electrons, so I'm pretty sure that the bromine would just be surrounding it. But let me just draw it as if it was 4 first. Okay. So now, with that being said, let's add the bromines. So we're going to add the 4 first. Okay. But it actually says 5 though. Okay. So now here's where I add the extra one. Give it a little bit of room there. Alright. So now we have all the bromines. And now let us go ahead and add the electrons. So phosphorus is actually sharing 5 of its 5 already, so we don't need to add any there. The bromines, on the other hand, are sharing 1 of its 7. So 2, 3, 4, 5, 6, 7. 2, 3, whoops. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, and now we can't forget that extra bromine. 2, 3, 4, 5, 6, 7. So if we just quickly count this out, hopefully we'll have 40 electrons. We have 8 times 8 times 8. Whoops, 8 plus 8 plus 8 plus 8, and then plus another 8. That is indeed 40 electrons. So that is perfect. So now technically we have the Lewis structure for this. The way to really, well, not verify, but just support more of our answer is just to make sure that we do the let's see, the no, it starts with N. No, sorry, formal charge. Let's start with N. Formal charge. Okay. So with that being said, okay, we have phosphorus likes to have 5 valence electrons. Okay. And it's right now sharing, well, it has 0 by itself, but it's sharing 10 of them. Okay, so that's a plus. And with that being said, that's going to be 0 because there's going to be 5 minus 5. And then on the bromines, okay, we have 7 valence electrons, but it has now 6 electrons by itself. That'll be 2 over 2. So that's 7 minus 7. That also equals 0. Okay. So that being said, we got our formal charges. We're all good to go. So theoretically, this right here should be the Lewis structure for PBr5. Let's see how we did. So exactly, circled it with bromines. They added 1 bond, and then they added the electrons. Okay, so this is correct. Okay, so with that being said, let's move on to the next question. Question 4. So for this, it's asking us to give the hybridization. Give the hybridization for C. And HCN. Okay. So now we have to find the hybridization. So the way I see hybridization, because it does involve actual chemistry components and really understanding you have to really understand the Vesper theory to understand hybridization. What I've come to notice though is that based on the amount of bonds, not type of bonds per se, with the amount of bonds you have, you fall to a specific range of hybridization. So for example, okay, this right here would be sp3. Okay, the reason being is because S would count as one of the 4 hybridization spots, and the P3 would cover every other 3. So now we have, if we did this now with the boron, and that would be sp2. Reason being, exactly, the S remains just one of them, and then there's two more left. So now what about an HCN? So that one is when now carbon will actually be in the middle. So we have HCN, okay? And because of that, we know that there's going to be one lone pair, but we should just establish the three bonds like that. So this is HCN. Now, what is this going to be? Based on what we just did, it only has two limbs, well, two appendages-ish from a carbon. So it can only use one of them as the S, okay? Leaving the other one as just the P. So with that being said, we have now SP. And that right there will be the hybridization for the carbon in HCN, okay? The answer would be E. That's the only one that has SP. So that means, let's see how we did. They agree it's SP. They show our picture. And with that being said, this is correct. So with that, now we're going to go to the next question here. Question number 5. So with that being said, we have a new question here. We have the molecular geometry is of BCl3, so that's boron chloride, if I remember correctly, is blank, and the molecule is blank as well. So with this one, actually, to be able to solve this question, we still need to know our Lewis dot diagram, okay? So if we look at our periodic table here to find out how many electrons we're working with, boron has 3 valence electrons, okay? And chlorine has 7 valence electrons. How did I figure that out? Is that boron is on the 13th column. To find out what electrons you have based on the 13th column to the 18th column, you have to make sure you just subtract by 10. So boron has 3, oxygen has 6, nitrogen has 5, things like that. So it only has 3. Chlorine, just as follow that same rule, would be 7. So we have 3 plus 7 plus 7 plus 7. So that's 21 plus 3, that's 24. So we have 24 electrons total. Okay? So, molecular geometry of BCl3. In order to do that, we just have to drop the Lewis dot. Okay? We're going to have the boron in the middle. And then we're going to just add these. And just a side note, boron can't follow the octet rule because it only has space to bond 3 things, okay? It'd be quite complicated for it to try to set up an octet rule. So we have BCl so now the last Cl. And with that being said, we should hopefully be able to count it and say there was 24 electrons, which there is, so perfect. Now, the molecular geometry of this, alright, we need to find out actually the hybridization. So, hybridization is found by the things attached to it, including lone pairs and more importantly bonds, okay? So for boron, we have 1, 2, 3 bonds, okay? So it will be sp2 hybridized because the S takes up one of the bonds, and then p2 because there's 2 more bonds left. So that'll be sp2 hybridized. And now that we know that, we can actually look at our electron geometry sheet, and it'll actually give us trigonal planar. Okay. Funny enough, because there is no lone pairs here, when you try to find its molecular geometry, this is also correct as well. And now, for that being said, we were able to cover that part. Now, whether it's polar or not, let's see. What is the electronegative difference between chlorine and boron? So the electronegativity difference from chlorine is 3.16 and boron is 2.04. So without even doing the math, I can say for sure that the is going to be a polar molecule. I mean, not molecule, polar bond, actually. And with there being a polar bond, we have to now look at what if it's counteracted. So if it's trigonal planar, it means that everything is done in an even 120 degrees, okay? So if everything is just pulling from the roots at 120 degrees each one, they actually all cancel each other out. So this is truly non-polar because of what they do when they cancel each other out, okay? And the molecular geometry discussed is indeed trigonal planar, okay? So that is what I would do there in regards to this question. We now figure out the molecular geometry, whether it's polar, and I hope that was a good explanation for it, is that because the chlorines are all pulling on each side evenly, that is why it ends up being a nonpolar molecule, even if its bond itself were polar. Okay, so now, with that being said, the only answer that works for this, whereas trigonal planar or nonpolar, the answer is D. Okay, let's see how we did. Trigonal planar, nonpolar, most structures like that, which is what we drew, and the distribution of electrons is what makes it nonpolar. So with that being said, the only one that worked for trigonal planar and nonpolar was indeed D. Okay. So with that being said, just quickly take a look at how we're doing. Okay. So, all right. We are doing great so far. So we're going to hop now into the next question after this quick water break. Okay. There we go. So it's going to be quite a bit of steps here, as you can probably see. It's about writing some chemical equation and then balancing it out based on its molarity. With that being said, let's get right to it. Question number 6. So first it's asking us, because there's a lot of text, I'm going to leave the question on this side, okay? So we have to write a balance, a chemical equation between H2SO4 and KOH balanced, okay? So that's the A. And that's called a neutralization reaction. So in a sense, what's happening is that there's a base being added to an acid to neutralize it, okay? And then B, we're now dealing with limiting reagents and seeing what happens when this is mixed together and how much is left of each one, okay? So it gives us quantity. So that's 0.650 liters of 0.430 molarity H2SO4, which is sulfuric acid, and KOH is potassium sulfate. Just to be able to, KOH is potassium hydroxide, okay? So with that being said, we have 0.600 liters of 0.240 molarity of potassium hydroxide, okay? So first let's balance the equation, okay? So H2SO4 and KOH. And it says to produce water and potassium sulfate. So sulfuric acid plus potassium hydroxide. Okay, it's going to neutralize to water, as they said, plus potassium sulfate. Now you're probably wondering why I put the 2 there in K2SO4. It's because potassium, alright, can usually just give up 1 electron. Alright, so in order for it to bond with the sulfate, which needs 2 electrons, because the sulfate ion needs 2 electrons, that's what we need there. And the biggest hint is because of this hydrogen here. So with that being said, actually, what we have to do here is first we're going to have to double the amount of potassiums we have. So that's 2 KOH there. Alright. And so now we have 2 OH minus, and we conveniently have 2 more hydrogens, okay? So that being said, we can actually now form 2H2O, because there should be 4 hydrogens in total and 2 oxygens. So that would be the second 2 right there. So this would be how you balance that out. So now we have our balanced equation. We can now assign the variables to them as they said. So we have 0.650 liters of 0.430 molarity. We have 0.600 liters, and we have 0.240 molarity. It's important to note the liters because when it's mixed together, we now have a new total concentration. A new total solution, which is a volume. There we go. New total volume, which does affect our concentration. So 0.65 plus 0.600, we have 1.25 liters total now, okay? This is going to play into an effect later. First, we need to find out how many moles were in each one, okay? So, if you remember our formula, we have, alright, molarity is equal to moles over liters. So, if you want to find the moles, it would be moles is equal to molarity times the liters, okay? So, we have now 0.430, alright, because that's going to be this one right here, times the 0.650. That's going to give us our moles, okay? So with that being said, our moles of H2SO4 was 0.2, let me use a different color, 0.2795. I'm going to repeat the process here for the potassium hydroxide. Alright, so we have 0.6 times 0.24, okay, and we get 0.144 moles, okay. So right away we can definitely see how the how the sulfuric acid is the excess and the potassium hydroxide is limiting, because we actually need 2 for every one. So if we only had 0.144, it can only react with really divided by 2, 0.072 of the H2SO4. In fact, our ratio right now, instead of it being even the 1 to 2, is gonna be, if we just divided the this by that, so right now it's 0.2795 divided by 0.144. Right now the ratio is actually inverse. It's almost a 2 to 1 ratio, and that is not something that we want, because that means that this is way in excess, because it's literally the opposite of what we actually needed. So that being said, now that we know the excess, we know how much KOH is going to react with the H2SO4. Like I said earlier, it's a 2 to 1 ratio. So if we have 0.144 moles of KOH, what's going to happen here is for every 2 moles of KOH, there's 1 mole of H2SO4, sulfuric acid. So you have to divide that by 2, which what we get is 0.072. So with that, that means that this right here, the 0.2795, is going to lose only 0.072 moles, okay? So that means we're going to have what's left. Let's see, 0.2795 minus 0.0072. We're going to have a whole 0.2075 moles left of the sulfuric acid, okay, after this neutralization. So this is not a complete neutralization, because we still have a lot more acid left, but based on just what we're giving, that's how much moles is left. But it doesn't ask for moles, it asks for concentration. So that's finally where we get to use our new liters value, okay? As this concentration formula says, molarity is moles over liter. So that divided by the 1.25 will give us our new concentration. Okay, so our new M for our sulfuric acid is now 0.166 molarity. Okay, so sorry if the work is all over the place, but the goal here, just as a quick recap, is that first, after we balance out the equation, we assign the values right under them. Okay, and then we're able to now calculate the moles for each one. We use that to see which one was the limiting and which one was the excess based on the ratios from the balanced equation. And then based on that, we're able to now subtract how many moles was actually used from the excess to see how much was left of the excess. And then when we got the amount that was left in moles, we then divided that by the new volume created by mixing those two volumes prior. So that is what we got. Hopefully you can see the steps here. They bounce out the equation to have 2 KOH and 2 H2O. And then they have this 0.2795, 0.144, yep, 0.2075, and they divide by the new total of the water, and they do get 0.166 concentration. So this is perfectly done. This is correct. Now let's move on to question number 7. It asks us to draw the Lewis structure for C2H3Cl. Show all unshared electron pairs and none of the atoms bears a formal charge, and all atoms have octets, except for the hydrogen atoms, which just have duets. Okay, so it's pretty much saying that this has to follow the octet rule, and there has to be no formal charge. And yeah, those are the two important parts. And you have to show the unshared electron pairs. So first, to be able to draw this Lewis structure, we have to first write down the question, C2H3Cl. So first, let's go ahead and see how many electrons we're working with in total. So based on the periodic table, okay, we have carbon, which has 4 valence electrons based on its position on the periodic table. It's on the 14th column. Hydrogen is on the first column, so it only has 1 electron. And chlorine is on the 17th column, so that's 7 electrons. So in total, we have 2 carbons, that's 4 plus 4, so 8, plus the 3 hydrogens, so that's 1 each. So that's 8 plus 3, that's 11. Plus now the chlorine is 7, so that's 18 in total. So 11 plus 7, that's 18. So we're dealing with 18 electrons. Okay. So now, the way I usually put the middle is the one that has the most unpaired electrons, because the way electrons, just like how carbon has 4 valence electrons, each electron there is unpaired. So I would put the 2 carbons in the middle. Okay. And I just have that because that solves one of its unpaired electrons. And now we have now H3Cl. So in order to have the most balanced out, I'm thinking that what I'm going to do is make each carbon carry 1 of the I'm going to make each carbon carry 2 of each of the molecules left. So we have H3Cl. So H, that's 3 hydrogens and 1 chlorine. That's 4 in total. So we have H, Cl. Now to fill in the rest of the electrons, the way I like to do it is that I start with the hydrogens, for example. It right now is sharing 1 of its only electrons it has. So hydrogen is complete. Chlorine is right now sharing 1 of its 7. So now we have 2, 3, 4, 5, 6, 7. So chlorine is now complete. Carbon right now in the middle is sharing 3 of its 4, so that's 1 more 4 here. Same with this carbon, 1 more there. So obviously this can't happen. The electrons need, or at least really want, to be able to be in pairs. So the way to resolve this actually is conveniently just by making them form another bond right there. So if we redo this picture now, we have carbon with a double bond in the middle, and then it's going to be now the chlorine here, the hydrogen, hydrogen. Then we fill in like that. But it asks us specifically to show all unshared electron pairs, which is what we've done here. I just like to show the shared ones as well. So this should be the Lewis structure. We're not done quite yet. We need to first calculate the formal charges. So with that being said, let's start with the carbons. So carbons, doesn't matter which one we pick actually, because it should be the same answer. It's right now sharing. Well, first we need the actual formula for a formal charge. It's going to be valence electron minus lone electrons, so lone E plus shared E over 2. That is the formula we're working with. So with carbon, valence electrons is 4, okay? It has no electrons by itself. It has no lone pairs, so it'll be 0. And the shared electrons is actually sharing with the surroundings, whichever carbon you pick, 8. So 8 over 2, bam. One of them, no formal charge. The hydrogens, okay, it's going to be 1 minus. It has no lone pairs, and it's sharing 2. So another 0. And now for chlorine, it has 7 valence electrons. It has 6 to itself, as you can see here, because 3 lone pairs, and it's sharing 2. And there you have it. All of them are 0. So this is indeed the Lewis structure for C2H3Cl. So yep, they've drawn it out. And actually, let me just say, because we have 18 electrons, we can just count it out. We have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we did use all of our electrons as well. Yep, 18 electrons. They filled it in. And this is what they should get. And they just replace the electrons with bonds. I like keeping the electrons there just to be able to visualize everything. But you can use either or to be able to draw your Lewis structure. With that being said, though, this is correct. And as I've already done the formal charges, based on how we have our same answers, we know that they do have the formal charges correct as well. So let's move on to the next question here. Question number 8. We have, what is the molecular geometry of IF5? So with this, it seems relatively simple because it's only asking just pick one of the A, B, C, or D, right? But in order to even answer this question, we need to first draw our Lewis structure. So there is quite a bit of steps involved, because to find the molecular geometry, we need to know what this thing even looks like, and we find that out by its Lewis structure. So let's find out how many electrons we're working with. Luckily, IF5, they're all halogens, all on the 17th column, so they all are going to have 7 valence electrons. So there's 6 atoms in total, 1 iodine and 5 fluorines. So in total, that's 6. So 6 times 7, we have 42 electrons to work with. All right. So now, considering that iodine is the only one that's different from the group, we're going to actually put that in the middle. Okay. Okay. So we have I, and we're going to now 2, 3, 4, and we're going to now add the aqua 1, 5. Okay, because iodine is one of the many atoms that can break the octet rule. So that's what we've done here. So iodine currently is actually sharing, as we count here, 1, 2, 3, 4, 5, 6. Whoops, sorry. If you only count individually, 1, 2, 3, 4, 5. It's sharing currently 5 of its 7 electrons. So to make up for it, is also just going to add 6 and 7. Sorry, I want to make it a little bit further away. It's going to have that. So it's really going to be surrounding itself in total with 4, 6, 12 electrons in total. So it is quite a full molecule. Fluorine, on the other hand, let's start with this one. It's sharing one of its 7, so it's going to be 2, 3, 4, 5, 6, 7. There we go. Same with this one. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. So if we were to count the amount of electrons there, we would actually see that we should have 42, because that's 40 and then 2 more. Because I just count based on what's surrounding the fluorines. We don't really count the iodine one because that already includes it. So it's going to be 8 times 5 because there's 5 fluorines, and the 2 more extra on the iodine. So that would be the Lewis dot diagram. Okay, so then with that being said, we then have to now make sure that we have the correct form by seeing this formal charge. So iodine in the middle has 7 valence electrons, and right now, as you can see, it has only 2 electrons to itself, that one lone pair, and it's sharing 2, 4, 6, 8, 10. So conveniently, that's 2 plus 5, that's 7. So this checks out. And for the rest of the fluorine surrounding it, it really is just going to be 7. It has 6 by itself, and it's sharing 2 of them. And so we both have 0. So this would actually be what the theoretical Lewis dot diagram would look like. So now with that being said, we need to identify its shape, starting with its hybridization. So the way you find a hybridization is to find out how many things are attached to it, whether it be lone pair or bond. Doesn't matter which type of bond, just a bond, period. And if you count, we have 1, 2, 3, 4, 5, 6. So 6 things are attached to it, okay? So that's going to be S, that's 1, 2, 3, 4, sp3, 5, 6, d2. You see, if this had a power, it'd be to the 1, so it's 1 plus 3 plus 2, it should add up to 6. So that's how you would write it there for the hybridization, meaning that this is going to be an electron geometry, okay, of octahedral. But this is the electron geometry. So if you picked A, that would be wrong. We need to then go ahead to see now what type of things are attached to it. We say that it's 6 based on how many things in general, but now what type? You have to split it into how many bonds, which is 5 bonds, and how many lone pairs, which is 1. Using this information now, we can find its molecular geometry. Now for this, I do not have it memorized, but it's important that you do if the course asks you to. But if you look at this, if you look at the Vesper theory, we have here, when it's 6, 5, and 1, it looks like this. Square pyramidal is what it's called. So exactly, as the picture shows, the iodine would be here, the lone pair would be down there, and everything else would be above, kind of like a square. And then it will form the pyramid with the last fluorine sticking up. So these ones would be like pseudo 90 degrees, and then there'll just be that lone pair bottom there. So if you look at it from a flat plane, it'll look kind of like this. The lone pair is down there, and that's what it's looking like. So this is what we call a square pyramidal. So like I said, this is now the molecular geometry. Octahedral would be its electron geometry, so that one would be wrong. So looking at that, when we look at these choices, the correct answer is actually going to be B, okay? That will be the molecular geometry of iodine pentafluoride, okay? There we go. They gave us a Lewis structure, and then they have the steric number, which is, they got a 6, which is what we're doing in terms of calculating the hybridization. And you can see here that based on this chart, because one of them is going to be a lone pair, we have the name square pyramidal. So the correct answer is indeed B. This is correct. So now look at question number 9, okay? We have, are the following polyatomic ions polar or nonpolar? Are these polar or nonpolar? Okay, so we're gonna write this down briefly. So we have NO2 minus SiF4 and Cl2. Okay, so now, oh, that NO2 plus. Sorry, I have to look a little bit closer for that one. Yes, that is an NO2 plus. Okay, so with this, to find out if they're polar or non-polar, we always have to draw our Lewis dot diagram. Okay, so we need to know how many electrons each offers. So nitrogen, okay, has 5 valence electrons based on it being on the 15th column, and oxygen has 6 valence electrons based on it being on the 16th column. Okay, but we have a plus. When you have a plus there, that means that we have 1 less electron to work with. So instead of it being 5 plus 6 plus 6, it's going to be that, but then minus 1 at the end. So that's 12 plus 5 is 17. Minus 1, we have 16 electrons to work with. Okay, so now I'm going to put nitrogen in the middle, surrounded by the oxygens. Okay, and there we go, 1, 2. And so now nitrogen is sharing currently 2 of its 5. So 3, 4, 5. Oxygen is sharing 1 of its 6. So 2, 3, 4, 5, 6. Same thing with this oxygen. 3, 4, 5, 6. But as you remember, 1 of the electrons is gone. So I'm going to just pick this one here, because that actually allows me to do what I'm about to do, which is create new bonds, which is what's going to happen with the nitrogen and the oxygen. So instead of there being single bonds between each one, it's a double bond between each. Okay, so now that we have it like this, let's first check we have 14 electrons. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16. I mean 16 electrons, sorry. So check, we passed that. And now we're going to make sure that we have the correct formal charge here. So nitrogen in the middle is going to be 5 valence electrons minus, has no electrons to itself and is sharing 8. So that's 5 minus 4. We have plus 1. So indeed, the positive charge here based on the NO2 plus is on the nitrogen, and the oxygen should be 0, but we'll check anyways. We have 6 minus, it has 4 to itself, and it has a bond with 4 electrons because of double bond, so that is indeed 0. So perfect. This is what we have. Now, because of this, based on the way nitrogen is, it has no lone pairs. It only has 2 types of things attached to it, which are 2 double bonds. But the hybridization for this, is sp. Okay, and we have a sp hybridization. Your form is actually linear. Now this is very important because a linear molecule means that the oxygens on each end, even though they may, actually not even may, if you look at the difference in electronegativity, 3.44 versus 3.04, it's just enough to where there is, you can argue that it is technically a polar bonds between them, but even if that was the case, the molecule itself still ends up being non-polar. Why? Because it's linear and the oxygens are pulling on the middle nitrogen both the same amount of force. So overall, there's no net movement. So NO2 plus actually would be non-polar. So which atom is closest to the negative side? So the way you answer this question is if there was a part that was more negative and more positive, then you would put the atom that's close to it. So let's say, for example, for some reason, one oxygen was more negative than the other. You'd still put nitrogen because nitrogen is the one in the middle. So it's technically the one closest to the other oxygen. The oxygens are separated by nitrogen. But in this case, because it's non-polar, we say this isn't applicable because both of them are equally quote-unquote negative. Even nitrogen is the positive end because it's being pulled apart by both equally negative parts. overall, you can't really say which atom is close to the negative side. I guess technically you could say it's nitrogen because we see that it is the positive side. That is going to be interesting. Because although the overall polarity is cancelled, the nitrogen itself is still technically the positive end. So, that's a good point. Well, I mean, no, the electrons want to be at both oxygen ends, so because they need to travel through nitrogen, it means that it also won't be positive. It'll still have the same charge throughout. So with that being said, I'm going to say it's not applicable here. So now SiF4, okay, we now have to first figure out how to even form this. So silicon is actually in the 14th column, so that's 4 valence electrons, and fluorine is in the 17th column, which is 7 valence electrons. So that being said, we have in total, fluorine is 7 times 4, so that's 28, plus the 4 more, so that's 32 electrons to work with for SiS4. And what's going to happen here, we're going to put the silicon in the middle, okay, and we're going to just do that, SiF4, so that's 1 bond each. And so silicon is already sharing 4 of its 4 electrons, so that one is done. And the fluorine is now surrounding that silicon. So with this being said, we can just check quickly the formal charge. Silicon is 4 valence electrons, and it's sharing, it has 0 by itself, but it's sharing 8, so that's 0. And fluorine, doesn't matter which one, because they all have 6, and they're sharing 2, that also equals 0. So both are correct. This is going to be the real, or the theoretical Lewis structure for this. So with that being said, is this polar or non-polar? So this, because as you can see right here, each end is going to be pulling the silicon with the fluorine, and because they're all fluorines, it's going to be all canceled out because they're all equally pulling the silicon. Because fluorine is quite electronegative, it's way more than the silicon. It is definitely polar bonds, but because we have a polar bond on each of the 4 ends, overall the net movement is also going to be canceled like the NO2+. So which is the more, now which side is closer to the more negative side? This is also not applicable because the electrons will be moving throughout. Even though quote unquote is not staying in the middle that often, there's still net movement going through. I would say if anything, I'm going to put a non-applicable dash for both. So this one will be nitrogen and this one will be the silicon. I'm still leaning more towards the not applicable because the electrons need to be able to move through the silicon or nitrogen to be able to get to their more negative ends. So now for the last one, Cl2. So this one is just 2 chlorines. Each one has 14 electrons, or 7 electrons, that's 14 total. And it's going to be Cl, Cl. So this one right away, you know for sure, they're going to be non-polar because they're both the same element, so they're going to equally pull at each other. Okay? And now for the last question, which is the atom close to the more negative side, this one is definitely not applicable. Of all the non-applicables, this one is the one that stands out the most, okay? Because these are now the same elements, so there's really going to be no negative or positive side. So I'm going to leave it like this for now. Let's see what our partner has. We have that it's a linear molecule, so although the bonds are polar, the bonds will cancel each other out. So the overall polarity will be 0, non-polar. This is also going to be non-polar, and this is going to be non-polar as well. So it doesn't really answer the question of which atom is close to the negative side. So with this, I would say that it's not really applicable, but if you were to say which where I guess the electrons spend the least amount of time. For at least the ones that do actually have polar bonds, you can say that that one, for example, the first one will be the nitrogen, the next one will be the silicon, and then the last one, that one's definitely not applicable because they'll spend equal time in any of the chlorines. Okay, so that being said, this is correct. Let's move now to question number 10. Okay, so we have, what is the Lewis structure of Br3 and why does it not follow the octet rule? Okay, so Lewis for Br3 and why not octet rule? So first you have to figure out how many electrons each element contributes. So boron is on column 13, so that's 3 electrons, and bromine is on column 17, and that's 7 electrons. So we have 7 times 3 because there's 3 bromines, so that's 21, plus that boron, so that's 24 electrons total. Okay, now before we just jump over to draw the Lewis structure, let's understand what's happening with boron. So as we said, it has 3 valence electrons, so it's going to look like this. So with the whole concept of bond, it's when pretty much one unpaired electron is able to now bond with or attach itself to another unpaired electrons. For boron, it cannot do the I guess octet rule because in its outer shell it only has 3 electrons. So there is no quote-unquote 4th electron for it to bond with something else in order to produce the octet rule. For example, look at carbon, okay? Carbon has 4 valence electrons like that. You see how it gives itself space to even do the octet rule? That will be a reason why. You would even see things like beryllium, for example. That one doesn't follow the octet rule because it only has 2 electrons, so it would only really be able to make 2 bonds, and it'll be completely satisfied with that. So that's just what we're dealing with here in regards to boron. Boron is just one of those. Typically when you're looking at the periodic table and it's before column 13, or specifically column 1, 2, and 13, because transition metals, those ones do very weird things. It can be quite unpredictable, but at least for columns 1, 2, and 13, they're completely, at most cases, satisfied with not following the octet rule, as you can see with boron. Okay, so that being said, now we're going to fill in the information. It's going to have 1 bond, as you said, 2, and 3, with the bromine here, and here, and here. Okay, and then we're going to figure out just by filling in the rest, because you see the bromines follow the octet rule, okay, but the boron doesn't. All right, because all I'm doing right now is filling in how many electrons are left, because right now the bromine shared 1 of its 7, so that's how we have 2, 3, 4, 5, 6, 7, and coincidentally that is following the octet rule for specifically the bromine, not the boron. And you can see here when we count the electrons, we do indeed have 24 electrons. So this checks out in every way. This is going to be the Lewis structure for boron well, I guess it would just be boron bromide, because boron is technically a post-transition metal. So that's what we have here. That's actually what we see in the picture as well. So the octet rule is satisfied for the bromine, but boron is an exception because it only has 3 electrons that it was able to share. So it only have 6 electrons total. So with that being said, just as how I showed carbon, that one would follow the octet rule. Beryllium wouldn't follow the octet rule. And there's really no way to redistribute this to where boron can follow the octet rule and something else in this molecule would. I mean, where boron would follow the octet rule, but then that would mean something else in this molecule wouldn't. So like for example, if you moved I guess an electron pair from here to here to where boron could follow it, now the bromine isn't following the octet rule, And it's even worse for the bromine because it actually started with 7 electrons. So it really just needed 1 electron to not follow the octet rule. So there's like no situation to where it would willingly want to even give up those 2 electrons, because like I'm already fully stabilized. Why would I want to transfer it over here? And boron on the flip side is like, I don't have space for this because I only had 3 lone electrons. So that is how we have this form, and that is why it doesn't follow the octet rule. So be on the lookout for things that are attached to other things that are in columns 1, 2, and 13. The most common one you see in column 1 typically is hydrogen. Hydrogen is a perfect example that doesn't follow the octet rule because it just has 1 electron to give. So it usually just forms 1 bond, just like that. So with that being said, this is correct. Now let's move on to the next question. With that though, let's take a quick little water break. Okay. Check how we're doing. We're doing good so far. Okay. So, question number 11. Lewis structure. What is the Lewis structure for C2HCl? Okay. So with this, first thing we have to do is, count the amount of electrons we're working with. So carbon is on the 14th column of the periodic table, so that's 4 electrons it can help. And because there's 2 of them, that's going to be 8 total. H, that's just in the first column, so that's 1 electron. And Cl is on the 17th column, which is 7 electrons. So in total, we have 8 plus 1 plus 7, which is known as just 8 plus 8, which is 16 electrons that we're working with total. So the goal is that whatever Lewis structure we draw has to have 16 electrons total. So now, because carbons have the most unpaired electrons, we're going to put those in the middle. So C and C. And we're going to just even distribute 1 on each side. That's the goal here. So H and Cl. So we're going to add 1 bond here. That's what we're going to start with. I'm going to add 1 bond to each one. And now we're going to see from left to right how many electrons left they would have. So hydrogen is already sharing 1 of its 1. So hydrogen is done. Carbon, based on both sides, is sharing 2 of its 4. So it'll be 1, 2, 3, 4. Same thing with this carbon here, 2 of its 4. 3, 4. Chlorine, on the other hand, is sharing 1 of its 7. So it'll be 2, 3, 4, 5, 6, 7. And there you have it for chlorine. It satisfied its octet rule. Now hydrogen does not want the octet rule because it only had 1 electron to begin with. So what do we do with these unpaired electrons so far? Conveniently, we can actually just throw them in to form a triple bond in total between the 2 carbons. So if we were to redraw this now, we would have carbon, 1 bond, 2 bond, 3 bond, and still the same thing for the outside places. Now effectively we've gotten rid of these unpaired electrons. And the cool part is that when you count at the end, we should still have 16 electrons total. Let's see. 2, 4, 6, 8, 10, 12, 14, 16. So this is what we're dealing with for Lewis structure. And if you want to draw it in a bond form, it would look like that. That is what the Lewis structure would look like there. Now, just to make sure we did this correctly, we do have the right amount of electrons, but let's see the formal charge, okay? So hydrogen here, its formal charge is done by getting its valence electrons, which is 1, minus the amount of electrons it has by itself, which is 0 right now, plus the amount of electrons it's sharing, which is 2. And because it's sharing, you have to divide that by 2. So we really just have 1 minus 1, So that's equal to 0. Perfect. Carbon, doesn't matter which one you pick, but the carbon, alright, has 4 valence electrons. And the reason why it doesn't matter because they're both doing the same thing, okay? They have 0 by themselves, but they're sharing 8 electrons because there's 6 in that triple bond and then 2 from the hydrogen or the chlorine, and that's how we got 0 as well. And the chlorine, last one, 7 minus, has 6 to itself plus 2 over 2. That is also 0. And now we have the true sense. Formal charge is where if there was any, where the charge would be. Because it was a neutral molecule, we want to make sure that we all got zeros here. Because if there's like a -1 or +1, we did something wrong. So with that being said, they calculate the amount of valence electrons. Then they're able to now draw it out with the Lewis structure, and they have exactly triple bond, the hydrogens, and the chlorine at the end. This is correct. So now time for question number 12. We have, is BRF5 polar or nonpolar? So let's first find out by actually getting the Lewis dot diagram of bromine pentafluoride. So the way we do that is by seeing how many electrons we're working with. So bromine and fluorine are both high halogens. So in a sense, we have 6 halogens total we're working with because 5 fluorines. So because there's 6 halogens, that's 6 times 7 electrons for each halogen. So in total, we're working with 42 electrons. So now because bromine is the only one that's bromine and the rest are all fluorines, we're going to put that in the middle. Okay? We're going to surround it by fluorines. 3, 4. I'm going to put the aqua one here, that 5th one. I'm going to just start adding the bonds. That's 1 bond there, 1 bond there, 1 bond here, here, and here. So that being said, right now, bromine, if we were to start there, is sharing 5 of its 7 electrons based on the fact that it has to share 1 with each fluorine. Because its valence electrons is 7, it still needs 2 more, which I've now added. So this now would be the bromine molecule in the middle. And fluorine is actually sharing 1 of its 7. So it'll be 2, 3, 4, 5, 6, 7. And that's what's going to happen for each one. And you see that we've now satisfied the octet rule for everything but the bromine. The bromine breaks the octet rule because of the fact that it's bromine. You'll see some atoms in the periodic table break the octet rule. Usually it's the bigger ones. For example, like bromine, it's here breaking the octet rule, where instead of 8, it now has 12 electrons surrounding it. So, with that being said, let's now check out to make sure that we have the formal charge done correctly. Bromine in the middle, it's going to be 7 valence electrons, and it's going to be subtract. It has only 2 to itself, but it's sharing a whole 10. So that's 2 plus 5, that's 7. So perfect. And the fluorines are all the same. It has 6 to itself, and it's sharing 2. Perfect. Okay, so that is done correctly. This is indeed the Lewis structure for it. So now, to say whether it's polar or not, we can actually just say right away that it's non-polar, but we have to make sure that we actually understand its molecular geometry. The reason why I say we can say that is because it has just one lone pair, okay? And because it has one lone pair, that already offsets everything. There's literally a lone pair that's unaccounted for in the distribution of the atoms around the bromine. So there's something already off there, okay? So, with that being said though, let's just go through and actually find the actual shape. So there's 6 things right now attached to the bromine. The reason why I say 6 is because there's 5 fluorines, yes, and 1 lone pair. So in total, that is 6. All right, and that hybridization is SP3, because that's 4 right now, because S is 1, and then plus 3 P's, and then D2. That is a hybridization for that. Okay, and things that are hybridized like this have an electron geometry shape of octahedral. Now, that doesn't give us our answer just yet. Actually, we have to now actually factor in what type of things are attached to it. So we do have 5 bonds, yes, but now, as we said, 1 lone pair. Okay, because of that, the shape is known as square pyramidal. All right, where if you kind of just put the well, if you redo it, bromine, you put the lone pair at the bottom, all right, and then you kind of have a square that kind of looks like this on a plane. So the lone pair is kind of under the plane. You have all the fluorines right there, and the last fluorine sticks out above the plane. Because now, if we drew it like this, where we have the bromine and we look side 2D, this is what the plane would look like. These cancel out, the fluorines on this side, but here's the issue here. The fluorine above and the bromine down here, I mean the lone pair, they're not the same thing. So there's already a difference in pull. So because of that, I'm going to say it's nonpolar. You can even look at the electronegativity difference. It's not that big. So in theory, they would be like, if it was just like a bromine, oh sorry, that's bromine chlorine. Bromine and fluorine, yes, that is a huge electronegativity difference. So because of that, they are all polar bonds, true. But now in order to see whether the whole molecule is polar or not, we have to see if all these polar bonds cancel each other out. And because of this lone pair, they don't. So knowing that, we can now say without a doubt that this is going to be a polar molecule, because our molecular geometry is square pyramidal, and as you can see here, it's not an even distribution between the fluorine and that lone pair. Okay, so this is what we have. As I said, square pyramidal, which is what I drew, and therefore it's polar and has net dipole moment pointing towards this fluorine up here, because of the fact that it's the more electronegative is a more electronegative between them, between bromine and fluorine. So now let's move on to question number 13. Okay, we have how many cups are in a quart? Nice. Okay, so to answer this question, we have to first understand where we're going from. So they said how many cups in a quart, so we're actually starting with quart. Okay, so let's say X amount of quarts is equal to, well actually not equal to, times some ratio would give us that in cups. So like it's gonna be quarts in the denominator and cups in the numerator, because by the quarts cancel each other out in terms of units, we're only left with cups. Okay, so now we actually have to see the conversion. If we have it here, we have in terms of units of volume, we have quarts, but we do not have cups, unfortunately. So let's use this here. We have 2 cups equals 1 pint, and 2 pints equal 1 quart. So this actually has an intermediary step, okay? So if we want to go from quart to cups, we have to first go from quarts to pints. So X quarts, and it's going to be quarts again in the denominator, to move pints in the numerator. And then now to get from pints to cups is going to now be pints in the denominator and cups in the numerator. So let's see what we're dealing with here. So 2 pints in 1 quart. Okay, that's what it says. And 2 cups in 1 pint. So if we now cancel out the units, we're left with cups. So we're going to multiply our numerator and multiply the denominator and divide the numerator by the denominator. And you'll see that for every quart, there's going to be 4 times of cups. That is what we are left with as the answer. So how many cups in a quart? We're going to just say, let's say we had 1.2 quarts for some reason. We just multiply that by 5. So we would have 4.8 cups in 1.2 quarts. Okay? So that's going to be the conversion here. So for this, they just did it the other way around, but they still have the same conversion to where there's 4 cups for every quart. So whatever value of x of quart, you would have 4 times the amount for cups. So this is correct. Let's move on now to question number 14. What is the Lewis structure? So we want the Lewis for XeF2O. So xenon fluoride oxide, okay? So this is going to be a little bit tricky, alright? Because xenon typically wouldn't care about making bonds because it's a noble gas. But let's solve this nonetheless. Let's see how we can work with this. In theory, xenon then will most likely be breaking the octet rule. But let's see how. So we have xenon, which is on the 18th column, so that's 8 electrons. It's using 8 valence electrons. And fluorine, 17th column, but there's 2 of them, so that's 7 electrons each, so that's 14. And oxygen is in the 16th column, so that's 6. So 8 plus 6 is 14, plus 14 again, that's 28 electrons total. So because xenon is the one that can break the octet rule most comfortably, I'm going to put that one in the middle, okay? And the reason why I say that, because even for it to even be involved in this Lewis structure, it has to already break the octet rule. So I'm going to use that to say that it's going to be in the middle with the benefit of the doubt. So xenon, and now, because I'm going to actually put, it's going to be 1 bond each for the fluorine, and the oxygen. So fluorine right now is sharing 1 of its 7 based on this single bond here. So 2, 3, 4, 5, 6, 7. Same here. So these two are already complete. Finish your octet rules. Oxygen is sharing 1 of its 6. So 2, 3, 4, 5, 6. So there's going to be 1 unpaired electron right now. Xenon, on the other hand, is sharing 3 of its 8. So there's going to be 4, 5, 6, 7. Actually, let me do it here. 6, 7, 8. So there you have it. Actually, let me put it up here. We have right now 1 unpaired electron. Okay. So with that being said, these 2 unpaired electrons are going to go ahead and form another bond. So between the xenon and oxygen, it's going to be a double bond. Alright? So if we redrew this, we have now xenon double bonded to this oxygen. Okay? And we have the fluorine here, a fluorine here. Oops, too close. Almost for the actual bonds. So fluorine here, fluorine here. Alright. And there we have it. But not quite. We want to make sure we actually finish up the xenon. So as you said, there was a bond here. It's going to have just an extra bond. This I'm going to write it over here like that. Just so we can make sure we know it's the extra one. Same thing with this one. I'm going to do that. So with that being said, though, that means that, in fact, I'm going to make this one red as well, because technically speaking, as you can see, it already, the blue ones are where the octet rule is, and the red is where it's going beyond the octet rule. So I just give that the oxygen xenon pair is the one that's following the octet rule. All right. So now if I calculate the formal charge for each one, fluorine should be relatively straightforward. It's going to be 7 valence electrons, and it has 6 electrons to itself, sharing just 2. So we do have 0. Okay. Xenon, 8 valence electrons. All right. It has 4 to itself, but it's sharing 2, 4, 6, 8. So that's 4 plus 4, 0. So that's perfect. Oxygen has 6 valence electrons. It has 4 to itself and sharing 4. So this is going to be the Lewis dot diagram for this indeed, because we've shown that the formal charges are good. And let's count the amount of electrons we have now. We have 8, 8, and then 8. So that's 8 times 3 is 24, plus 2, plus 2. That is indeed 28 electrons. So, as they drew it. They do have a double bond there for the oxygen, which is what we had, and they filled in the electrons. So as you can see, those 2 that I added break the octet rule, which is what they have here, but everything else is following the octet rule. So this is correct. And they also use the formal charges to be able to justify why they broke the octet rule, because the goal is to have 0, especially when dealing with a neutral molecule. You want to have 0 for everything. So by us being able to even calculate 0 for xenon, that shows that it would prefer to have that formal charge of 0 rather than to just strictly follow the octet rule. Okay, so now let's go on to question number 15. All right. Wow. So this is going to be a multi-step question. Just going through in terms of it seems that we have excess and limiting, and then it's going to ask us, like running an experiment, if this is how much was produced, what will be the actual percent yield. So just start from the beginning. Okay, so we have 45.15 grams of P4. Okay, and they do give us a molar mass, which is 123.90 grams per mole. And when they give us the molar mass, we use that number in our calculations. We don't go back and then do it again in the periodic table. Okay? And the other one they have is this mixed with 131.5 grams of Cl2. And the molar mass here is 70.91 grams per mole. Alright? And now, based on this equation they gave us, we have P4 solid plus 6Cl2 gas turns into 4PCl3 liquid. Luckily for us, this is already balanced out, so we're good to go, as they said. And now the first question they ask, how many grams of PCl3 can be produced from this reaction? So the molar mass of PCl3 is 137.33 grams per mole. So let's just tackle question A first, alright? Okay, because we need to figure out how many moles we're working with, alright? So, with that being said, we have 45.15 grams, and the molar mass is 123.90 grams per mole. The formula to find moles for molar mass, okay, so the molar mass is moles per per mass. Okay, that's a molar mass. Sorry, whoops. It's the other way around. It's mass per mole, per 1 mole. So if you wanted to find the moles for it, okay, we'd actually divide the mass given by that, because then the mass will cancel out and it would just be left 1 mole. So look kind of like this: mass times 1 mole per the amount per mole. Okay, so that's what we're going to do here to find the moles of each one. So it's going to be now 45.15 divided by 123.90. So we have 0.364 moles. Okay, and the same thing for the other one, 131.5 divided by 70.91. We have 1.854 moles. Now with this information, to see how much is produced, okay, we first need to find out what the ratio is for the reactants. As you see here, because there's no coefficient here, but there is here, it's 1 to 6. So that means the Cl2 has to be 6 times, at least 6 times greater for it to be considered the excess, that there's too much of it. So if we did the 1.85 divided by the 0.36, we should hopefully get a number of 6 or above. But funny enough, the ratio here, when you divide this by 0.364, that's equal to 1. That's equal to 5.0. So instead of it being a 1.6, it's 1 to 6 ratio, it's a 1 to 5 ratio. So let me just add the moles right under so you can keep track. 4 and 1.854 moles. So funny enough, even if it looks like we have so little of the tetraphosphorus, that's actually our excess, because of the fact that instead of it being 1 to 6, it's 1 to 5, meaning that all of that chlorine is actually going to be used up. So because chlorines are limiting, we're going to use that to figure out how many moles of PCl3 was actually made. So we have 5 moles of it, right? And the ratio here is 6 to 4. So we're going to do, to convert it to the 4, we're going to divide by 6, because that's going to be, in a sense, how many chlorines it takes, and then multiply by 4. And that will give us the actual moles of, sorry, I definitely did not need to do that. I need to actually use a 1.854, not the 5, because the 5 was just for the ratio. So it'll be 1.854, okay, divided by 6 times 4. And we get 1.236 moles produced, okay? And they're gracious enough to give us the molar mass. So here we just multiply together. So it's just be the moles times the molar mass to where the moles can cancel out. And we should get our grams. So 137.33. The amount of grams produced here is going to be 169.78, which is 169.8 grams. That's going to be how much of the product will be produced. So with that being said, we did establish that our tetraphosphorus was our excess. Okay, so how many grams of the reactant will remain? There's no more chlorine because that one was our limiting reactant. That one's gone. Now we have to figure out how much did it then use of the P4 since it was in excess. So we can go back to our 1.85 number. I'm going to do the same thing where we divide by 6 and we multiply by P4's coefficient. But as you can see there, it's a 1. So we're really just dividing by 6 to see how much was used. So we actually, according to this, when we divide by 6, we used 0.3091 moles. So conveniently, it's less than the 0.364 as we predicted. So now we subtract to see how much is left, 4 moles, okay? So that is 0.055 left of the moles. And then now we convert it back to grams by what we did earlier, just multiplying. So multiply that times the 45.15, and we get our answer for B, which is 2.498 grams of P4 left. Okay? Now, the last question, if the actual yield was 101.2 grams, what is the percent yield? So the percent yield, okay, is calculated by what's it called? Experimental over theoretical. Actually, sorry. Experimental minus theoretical, the absolute value of it, times 100%. Okay, so the absolute value difference over the theoretical, which is what we calculated, and then times 100%. So in this case, it's going to be 101.2, all right, minus the number 169.78 divided by, remember it's the absolute, so it's no longer a negative, divided by that much. So we have quite a bit of a big percent yield, because we multiplied that by 100. We have a whole, as we've calculated, 40.39% percent error. So the percent yield then would actually be how much we got based on that. So it will be 100 minus that answer, because I was already thinking of percent error, but percent yield is the other way around. So we have actually a 59.606 or 61% yield. So this would be more percent error. So percent yield is found by experimental, well, it's going to be theoretical then minus experimental. So let's flip these around. Minus experimental. So that is what we're going to have for C. So just to make sure, this is going to be the yield. The one above was the error, because that's how much room there was in terms of what we had gotten wrong. So let's see how we did here. Based on this, yep, 0.3644. That is how much we got, and 1.8545. That is also what we got for the CL2. And then they should see that our limiting was indeed, just to make sure that we do this right. Yep, 169.79, which is what we got. How many grams of the reactant is left in the thing? So the excess will not remained, so they subtracted it, yep, and they got 0.055. But then here, as you can see, the P4 mass, oh, whoops, I multiplied by the wrong one. I definitely should have done, because I multiplied it by the 45.15, so that's why it was different there. So we have 0.55, multiplied by the molar mass is 123.90. So we actually have here, as the answer says on there, so it's good that we checked our work, 6.855. Yep, perfect. And the percent yield, it's actual yield over theoretical yield. Okay, so I was calculating the percent error. So with that being said, percent yield is just simply just the actual over theoretical times 100. So this right here, I'm going to fix this to say percent error, which is also used as well. So we're going to leave that there for now, but not put it as C. We're just going to leave that. So percent error, as I said earlier, was experimental minus theoretical over theoretical. But percent yield, which I'm going to put in blue here, is, as they said, just experimental over theoretical times 100%. So it's just face value right there. Experimental over theoretical times 100. So we have, just how they said, we got 101.2 divided by the answer, or divided by 1.69. Our percent yield is going to be 59.61% yield. So there you have it. And now our answers match. So just as how I did, just be careful that you are multiplying with the correct numbers, because that molar mass was a big error that would have definitely confused a lot of things. Luckily, we had a base to go off. And once again, the percent yield is just experimental over theoretical times 100. Okay, so So that's correct. Let's move on to question number 16. But before that, let's take a quick little water break, see how we're doing. Okay. All right, we're doing good. Okay. So let's switch back over. And let's see now. We have, what are the Lewis structures for the following compounds: NO2 plus and NO2F. Okay. So first, let's just tackle the NO2 plus. All right. So nitrogen has 5 electrons because it's on the 15th column. Oxygen has 6 electrons because it's on the 16th column. So each one, this one will be donating 5 electrons in the valence. Oxygen is 6 times 2, that's 12. But this plus right here means that we're actually going to have 1 less electron to work with. So rather than just being 17, we're actually going to work with 16 electrons. Okay, that right there is important because that actually tells us whether we're approaching this correct or not. So that being said, let's just go straight to the Lewis structure. We're now going to have N in the middle, all right, and then the 2 oxygens on each side, and we're now going to add the bond there. Okay, so now the oxygen is sharing one of its 6, so 2, 3, 4, 5, 6. Same thing here, 2, 3, 4, 5, 6. Okay. Nitrogen, on the other hand, is sharing 2 of its 5, so 3, 4, 5. But as we said, there's 1 electron less. I'm just going to take off this one here. What this allows me to do is see this and see there's 4 unpaired electrons right now. So I can actually use these to form a double bond between each oxygen and nitrogen. So if I redrew this, it would actually look like this. Okay, just redo that. Okay, we have the oxygen, we have the other oxygen, and there's nothing on the nitrogen anymore, and we have now a complete oxygen on each side. Okay, and if we went ahead to do the formal charges, the oxygen would be 6 valence electrons minus. It has 4 to itself, 4 electrons, and it's sharing 4 for each oxygen, so that is coincidentally the 0. Perfect. The nitrogen, on the other hand, 5 valence electrons. It has 0 to itself and is sharing 8. So that is indeed plus 1, which is how NO2 is a plus 1. It's actually on the nitrogen. So this is indeed the Lewis structure for NO2 plus. Now, they do ask us to include all the important resonance forms. So in order for this, there are possible forms, but if I drew that resonance, it would no longer be following the octet rule. For example, if I moved, if I moved one of the double bonds, okay, to make it into a single bond, and the oxygen was like this, there was just 1 bond between them, and now nitrogen had that. Although this could be a resonance form, this doesn't really work because this oxygen here is no longer following the octet rule. So this couldn't really work. And even the nitrogen wouldn't be either, because now it has 10 electrons instead of 8. So that wouldn't be it. So looking at this, this is the most stable and frankly probably the only resonance structure it can form, because any other thing would break the octet rule. But let's look at NO2F now, okay? we were given a lot of hints based on just the NO2, but to see what NO2F is, let's find out. So that one would be, as you see here, we have to first count the electrons. It's going to be 5, 12, and fluorine is on the 17th column, so that's 7 electrons. So actually now we have 17 plus 7, that would be 24 electrons total. Okay? So now with that being said, we're going to put the nitrogen in the middle again because it has the most unpaired electrons. And we're now going to surround it with the 3 things. So we have O, O, and F. Okay? So now oxygen is going to be, well, it's going to have 2. Sorry, I'm blanking out. Oxygens now have sharing one of its 6, so that's going to be 2, 3, 4, 5, 6. Same thing here, 2, 3, 4, 5, 6. And now the fluorine is going to be 2, 3, 4, 5, 6. Oops, too close. 6, 7. And the nitrogen is right now sharing 3 of its 5, so 4, 5. So the only lone pairs here are these 2. Whoops, yep, this one here and that one there. So we have to figure out a way to take care of this. Nitrogen is already full, so that one wouldn't work. But what we could do actually is that if we kind of split this and just gave an electron to the oxygen, well actually, if we made this one into a bond here, so these ones bonded together, and we just gave this electron to this oxygen, we could fit our octet rule for everything here. So what we would have now for our picture, and just to make sure I'm doing things right, I'm actually going to go ahead and count the electrons for the previous question, because we do have 4, 8, 12, 16, perfect. Okay, so now we have the nitrogen here. Okay, we have this bond still, this oxygen above, comfortable now with its octet rule because it just took that one electron, and this oxygen here comfortable as well with the octet rule because it has the bond, and the fluorine just staying as a fluorine. Now with that being said, this one now can have possible resonance structures. As soon as I just move this out the way, this work out the way, put this under here. So what I mean by resonance structures, let's find the formal charges of each. So first thing, the oxygen to the left, that one's going to be, as we did, 6, okay, minus, has 4 to itself, plus 4 over 2, so that is 0 still, perfect. The oxygen above, it's still 6 valence electrons, but now it has 6 to itself, and it's sharing 2. Okay, so that one would be, not 0, sorry, it'd be minus 1. So that oxygen above has a negative 1 charge. But that means something here has to have a positive charge. Let's check the fluorine. So the fluorine is going to be 7 minus, it has 6 to itself, 2 over 2. That's going to be 0 as well. And now the nitrogen has, it's going to have, sorry, I'm blanking out, 5, and it actually has 0 to itself, and it's sharing 8. So that's going to be 4, so that's going to be plus 1. And that's where our positive charge is to cancel it out. So we have a minus 1 and a plus 1. So now, similar to the other question to how we could not make it in a way to where the nitrogen would be able to fill its octet rule, that one is not going to be bothered with the formal charge differences. We're going to just start rearranging everything in terms of the resonance structure. So this is one resonance structure. Another one would just be to make negative on the other oxygen. Okay, so that would be, we switch these around. We have now the oxygen single bonded here at the end on the left with the nitrogen, okay, and then this one's the one that has a double bond. that is another possible resonance structure, because now the negative is going to be here, the positive is still on the nitrogen. Now there is another resonance structure we can do as well that's a little bit wonkier, okay, is if we made it so that the both oxygens actually had a single bond and there was a double bond with the fluorine, okay? And you notice that at the end of the day, everything should still add up to 0 for the formal charge. So as you can see, pretty much all I've been doing is moving a double bond to, like, as in making it take the whole double bond, and then also making something else give up its lone pair to form a double bond. That's how I move it around. But fluorine now, because that happens, you would actually calculate its formal charge. You would see that this now is going to be 7 minus, okay, it has 4 to itself, and it's sharing 4. So it's actually going to be a plus 1. And so you'll see here that just as how we have now 2 minus 1s for the oxygens, nitrogen still stays plus 1, but so is the fluorine now. We have 2 minus 1s and 2 plus 1s. These are, at least from what I can see, all the possible variants of the formal charges you can have that still follow the octet rule for NO2F. So let's now check and see how we did. Okay, we have, let's see here. Ah, okay, I see what they did now in terms of this. The way they did that is that they moved it to form a triple bond. Ah, so they put the bond in there, so it still follows the octet rule, and they kick the bond out. That makes sense. So just as how we did here, there are actual little structures we can do, just as what they did there. So it's important that, just as how I was struggling earlier, you want to make sure that when you do move a double bond into the, I guess, the outer part, when you move a pair out, you have to push a pair in. So one of them, as they showed there, will be oxygen, now with a single bond between the nitrogen, but that means this one has to be a triple bond, because this oxygen is going to be the negative, and this oxygen is going to be a positive. And you'll see that in total, we have positive here, negative here, and that's going to be a plus 1 total. And if you inversed it, it still counts as a different resonance structure, because now it's going to be oxygen on the right that has the single bond. So we have now positive here, and a negative there. So we have 3 resonance structures here. And then for this one, exactly, we do have the 2 resonance structures as they mentioned, where it just keeps switching. But exactly, this will be the 3rd proposed resonance structure, to where the fluorine is the one that has double bond, because it still follows the octet rule. This is just the one that's the least favored, so this one will be the least favored, because of the fact that now fluorine, which generally just prefers to have, a charge of like 0, as you can see, this form here has the most, I guess, different formal charges, to where there's like, you want the formal charge to be as close to 0 as possible, as you want as many zeros as possible in your formal charge calculation. And this one's just all over the place, to where it's like plus 1 here, minus 1 there. So that's why this one wouldn't work. Now, in regards to this, as we mentioned, when we kick a double bond out, it has to be replaced somewhere. So these are all the variants of the formal charges here. So this is correct. Although they are missing one form with the fluorine, technically they did show me the other 2 here that I was missing. So just make sure that you account for every possibility, meaning that try your best to see what happens when you move a pair out, as in towards one of the outer atoms, and then move a pair in from just any other of the outer atoms as well. So that's it for number 16. Let's see now what we're doing. We have number 17, which is relatively straightforward. It's asking if, I'm going to stop here for today, but just ask number 17, is there a charge in H2O? So for this one, we can actually approach it in different ways. We can use the oxidation numbers, or we can use its formal charge as well. Because oxidation number is relatively straightforward, we have H2O. Funny enough, there's actually rules for it. So oxygen likes to be -2, except for in hydrogen peroxide, which this is not. So we have a formal charge of -2, -2, and we're assuming here, actually, oxidation would not work because that assumes that we have a net charge of 0. So instead, we're going to use our formal charge. So with that being said, to use formal charge, we need to find its Lewis dot diagram. H2O, H in the first column, so that's 1 electron each, that's 2 electrons. Oxygen, 16th column, 6 electrons, so we have 8 electrons total. Okay, so now we're going to put oxygen in the middle. We're single bond with the hydrogens. So with that being said, the hydrogen is actually now complete because it's sharing one of its 1 electron, so we don't need to add any more. But oxygen is sharing right now 2 of its 6, so 3, 4, 5, 6. Okay, so this right here would actually be the completed version of what a Lewis structure for oxygen would be. There would be no moving around the electrons because of the fact that hydrogen actually doesn't want to take more. I don't think it even can. So with that being said, there's no way to move anything else. Let's calculate on the formal charge. So the way you calculate formal charge is done with this formula: valence electrons minus, okay, and then parentheses, not really lone pairs, but electrons not shared plus electrons shared over 2 though, and that is going to be your formal charge equation, and the goal is to have it equal to 0 hopefully, or else it means it has a charge. So if we do the hydrogen first, we have 1 minus, it has no electrons that it's not sharing, so that's 0, and it's sharing 2 electrons, so 2 over 2, that equals 0. Perfect. And now for the formal charge of oxygen, so this is hydrogen, oxygen is 6 valence electrons, it has 4 by itself, and because they're sharing 2 on each side, that's 4 in total. So that indeed does equal 0 as well. Okay, so because the formal charges for both are 0, this means that H2O, water, has no charge. So the answer is no. Okay, and that is what they got here. They used the oxidation states, but the oxidation states is assuming that we have a net charge of 0. So that one can be good to use, but I would actually go with the formal charges because that at least allows us to use a concrete information that we're given to be able to find that. So with that being said though, we're going to stop here for tonight. Just want to thank you again for joining me this evening. If you had any questions or want to go over the topics that we reviewed tonight, don't hesitate to click on the links in the description below. We have many resources and tutors available for you. But other than that, thanks again for joining me in this stream. You have yourselves a wonderful night and take care.